Before we get into this one, if you enjoy these deep dives into science and reality, a quick like or subscribe goes a long way. It is a small thing on your end, but it genuinely helps this channel keep going. Now, let's begin. Tonight we are going to talk about the most important prison in the universe. You cannot see it, you cannot break into it, and the prisoners inside have never once escaped, not in the entire history of the cosmos. The prison is not a law in the human sense, it is a feature baked into the structure of reality itself. Deeply understood through quantum chromodynamics, confirmed by experiment, but without a complete rigorous proof from first principles, one of the hardest unsolved problems in mathematical physics. The prisoners are quarks, the building blocks of protons and neutrons, the building blocks of atoms, the building blocks of you. You have more quarks in your body than there are stars in the observable universe. Every proton has 3. Every neutron has 3. Every atom in your body has protons and neutrons in its nucleus. The number of quarks in a single human body is somewhere around 10 to the power of 29. A number so large that if every grain of sand on Earth were a trillion, you still would not reach it. Every single one of those quarks has been imprisoned since the first microseconds after the Big Bang. Not imprisoned by a wall, or a cage, or a force that weakens over time. Imprisoned by the fundamental rules of the universe. Rules that get stronger the more you push against them. Not locked in by walls, locked in by a force. A force that does something no other force in nature does. Instead of weakening as the quarks move apart, it gets stronger. The further you try to pull a quark away, the harder the force pulls it back. And if you put in enough energy to actually separate them, the energy you spent does not free the quark. It creates 2 new quarks, 2 new prisoners, both locked up immediately. You cannot win. You cannot separate quarks. Not with the most powerful particle collider on Earth. Not with anything. And CERN, in a series of experiments that produced results physicists are still trying to make sense of, briefly recreated the kind of deconfined state that existed in the first microseconds after the Big Bang. Not a state in which individual quarks float silently alone. A dense, violently interacting medium in which quarks and gluons were no longer locked inside individual protons and neutrons. A quark-gluon plasma. The same state the universe passed through before matter as we know it came into existence. Not free for long, not by any human measure. For a tiny fraction of a second, at temperatures 10,000 times hotter than the centre of the sun, inside the most sophisticated detector ever built, the prison walls dissolved. What physicists found inside those walls is stranger than almost anything the textbooks predicted. Tonight, we go inside. Before we get started, if this is the kind of science that makes the world feel stranger and bigger than it did before, subscribe. It helps this channel reach the people who need to hear this. Now let's talk about the strangest property of the most important force in the universe. There are 4 forces in nature. Gravity holds planets together. It keeps you on the ground. It binds galaxies into clusters. But gravity is extraordinarily weak at small scales. 2 protons sitting next to each other feel almost no gravitational pull between them. The force is real, but it is negligible at the scale of atoms. Electromagnetism is what holds electrons around atoms and lets molecules form. It is what makes light, drives chemical reactions, and powers every electronic device on Earth. Electromagnetism gets weaker with distance. The further apart 2 charged particles are, the less force they feel. The weak nuclear force governs certain types of radioactive decay. It is short range and relatively feeble. Then there is the fourth one, the strong nuclear force. And the strong force is different from everything else in a way that should not be possible. The strong force gets stronger with distance. Let that sit for a second. Every other force you have ever heard of weakens with distance. Gravity from the Sun is weaker at the edge of the solar system than at Earth's orbit. A magnet pulls harder when it is close than when it is far. Light from a candle dims the further you walk away. This is how forces work. Distance weakens them. The strong force does the opposite. Inside the confinement regime, pulling two quarks apart stretches the gluon field between them. The energy stored in that field grows with the separation. The harder you pull, the more energy builds up in the field. It is as if they are connected by a rubber band that never breaks. Except it is not a band, it is not a string. It is a field of colour charge doing something that no other force in physics does. Think about why this matters for the experience of everyday life. Gravity holds the Earth together, but it weakens as you move away. Stand on top of a mountain and you weigh slightly less than at sea level. Move to the moon and you weigh even less. Gravity extends across all of space, but it fades. Electromagnetism is the same. Move two magnets far enough apart and they stop attracting each other. The further you go, the weaker the pull. The strong force does not follow this rule. The strong force is one of only two forces that operates differently at different length scales, becoming more powerful as the distance grows. This behaviour has no analogy in the forces you can feel or measure in daily life. There is nothing else in nature that works this way at the human scale. And because of this behaviour, an atom is fundamentally different from what most people imagine. It is not a solar system in miniature, with hard particles orbiting a hard centre. It is a system of permanently trapped things. The centre of every atom contains prisoners, held inside by the strongest force in the universe, a force that strengthens when they resist. Physicists have a word for this behaviour. They call it asymptotic freedom at short ranges, where at very small distances the quarks are actually somewhat free, moving around loosely inside the proton. But at longer ranges, the force tightens its grip. This behaviour has a name too. It is called confinement. Quarks are confined. Permanently, by design. That sounds like a physics fact. Something to memorise and move on from. It is not. It is the most important structural feature of the universe. Every atom, every molecule, every protein, every cell, every organ, every object you have ever seen or touched. All of it exists because quarks are trapped. The confinement is not a detail, it is the foundation. If confinement did not exist, protons and neutrons would not form. If protons and neutrons did not form, atoms would not exist. If atoms did not exist, chemistry would not exist. If chemistry did not exist, you would not exist. Everything rides on a force that works backwards. Now here is where it gets strange. If you try to pull two quarks apart by pumping energy into them, what happens is not what you expect. You do not liberate the quark, you create new quarks. The energy you pour in does not break the bond. It creates a new pair of quarks from the energy itself, one for each end of the attempted separation. Instead of one free quark, you now have two new quark pairs, each immediately bound to a partner. The universe does not allow isolated quarks to exist. It is not a restriction imposed by the current state of technology. It is a rule of nature. As far as anyone has ever observed, a single free quark has never existed in isolation, not once, at any point in the universe's history. except for one very specific set of circumstances, the first microseconds after the Big Bang, and the inside of CERN's most powerful experiments. Before we go further, you need to understand what quarks actually are. You have heard of atoms. Atoms are the building blocks of chemistry. Every element is a type of atom. Carbon atoms make up most of the molecules in your body. Oxygen atoms in the air you breathe. Iron atoms in your blood. For a long time, atoms were thought to be the smallest things. The word atom comes from the Greek for uncuttable. Then physicists discovered that atoms have structure. Each one has a nucleus at the centre, surrounded by electrons. The nucleus is tiny but massive, holding almost all the atom's weight. The nucleus is made of protons and neutrons packed tightly together. That held for a while as the bottom of the list. Electrons, protons, neutrons, 3 types of particle, and that was physics. Then in the 1960s, experiments began suggesting that protons and neutrons were not fundamental either. When physicists fired electrons at protons at very high energies, the electrons bounced back in ways that only made sense if the proton had internal structure. Something inside the proton was deflecting the electrons in sharp angles. Something point-like, small, hard. This experiment was done at the Stanford Linear Accelerator Center in California. The result was deeply unexpected. The assumption at the time was that the proton was a smooth, uniform blob of charge. If it were uniform, electrons fired at it would bounce back gently, like a ball hitting a soft surface. Instead, some electrons bounced back at enormous angles, as if they had hit something dense and hard inside the proton. The physicist Richard Feynman described this situation with characteristic clarity. The electrons were not bouncing off the proton as a whole, they were bouncing off specific, point-like constituents inside the proton. He called them partons. Other theorists called them quarks. This discovery earned the Nobel Prize in Physics in 1990. It established definitively that protons are not elementary particles, they are composite objects, and the things inside them, the quarks, are what the strong force operates on directly. The implication is startling. Every time you hear about atoms being the building blocks of matter, remember that atoms are built from protons and neutrons are built from quarks. The actual fundamental building blocks of atomic matter are one level deeper than most people ever hear about. The physicist Richard Feynman called them partons. Other theorists had proposed them independently and called them quarks, a name borrowed from a line in a James Joyce novel. The experiments confirmed they were real. The proton is not a fundamental particle. It is a composite object made of 3 quarks bound tightly together by the strong force. A neutron is also made of 3 quarks, but a different combination. Proton, 2 up quarks and 1 down quark. Neutron, 2 down quarks and 1 up quark. These names mean nothing. Up and down are just labels. Quarks come in 6 types, called flavors: up, down, charm, strange, top and bottom. The names are arbitrary. What matters is what they do. What they do is combine to form protons and neutrons. And protons and neutrons combine to form atomic nuclei. And atomic nuclei plus electrons form atoms. And atoms form everything. The chain goes, quarks, then protons and neutrons, then nuclei, then atoms, then molecules, then you. This chain is worth slowing down on. Physics understands each link separately. Quantum electrodynamics describes how electrons bind to nuclei. Nuclear physics describes how protons and neutrons combine into stable nuclei. Quantum chromodynamics describes how quarks combine to form protons and neutrons. But the chain does not run cleanly from the bottom up. You cannot start from the equations of QCD and derive the colour of copper or the melting point of ice. The complexity at each scale is so large that direct calculation from first principles becomes impossible. The connection between the quarks in your atoms and the properties of the molecules in your cells runs through layers of physics that each must be approximated, simulated, and studied separately. Everything in your body is a collective consequence of rules operating 2 levels deeper than chemistry. The quarks in your cells have never been directly observed by any instrument. They reveal themselves only through the properties of the protons and neutrons they form. The ground floor of matter is permanently hidden, and the force that hides it gets stronger when you try to look. Quarks are the ground floor, and they are locked inside their particles by a force that physics can describe mathematically but cannot fully explain from first principles. This is not a minor gap. The mathematical theory of the strong force, called quantum chromodynamics, or QCD, is one of the most successful physical theories ever developed. It correctly predicts hundreds of measurements to extraordinary precision, but deriving the fact of confinement directly from its equations from scratch, without assumptions, remains an unsolved problem in mathematics. It is one of the Millennium Prize problems, a set of 7 mathematical challenges offered by the Clay Mathematics Institute in the year 2000, with a prize of $1 million each. Proving why quarks are confined rigorously from the mathematics of QCD is still worth $1 million. Nobody has collected it. The most successful theory in the history of particle physics contains a central feature that nobody has fully proven from the ground up. Quarks are not just particles. They carry something unusual. You know about electric charge. Positive and negative, like charges repel, opposite charges attract. Protons are positive, electrons are negative. The electromagnetic force runs on electric charge. Quarks carry electric charge, but they also carry something else. Something that has nothing to do with electricity. Physicists call it color charge. The name is deeply misleading. Quarks are not colored. They have no actual visual color. The word color was chosen as a label because there are 3 types of color charge, and that reminded physicists of the 3 primary colors of light: red, green, and blue. But quarks are not red, green, or blue in any physical sense. These are just labels for 3 distinct types of a property that has no everyday equivalent. Here is what matters. A quark can carry red color charge, green color charge, or blue color charge. When 3 quarks come together to form a proton or neutron, one of each color is present. Red plus green plus blue, in the color analogy, combines to white. A proton is color neutral. It has no net color charge. Color charge cancels inside it. This matters because the strong force only operates on objects that carry color charge. Protons and neutrons, which are color neutral, do not strongly interact with each other in the way quarks do inside them. The nuclear force that holds the atomic nucleus together is a residual effect of the strong force, like the faint electromagnetic influence that sometimes extends from electrically neutral atoms when the charge distributions are slightly uneven. The actual strong force, the one acting directly on color charge, is confined to the inside of protons and neutrons. It is the most powerful force in nature, and it operates only inside particles smaller than atoms. The carrier of this force is a particle called the gluon. The gluon is to the strong force what the photon is to electromagnetism. Photons are particles of light, and they carry the electromagnetic force between charged particles. Gluons carry the strong force between colored quarks, but gluons are strange in a way that photons are not. Photons carry no electric charge themselves. They are the carrier of the electromagnetic force, but they do not feel that force directly. Gluons carry color charge. They are the carrier of the strong force, and they feel the strong force themselves. A gluon interacts with other gluons. Gluons bind to gluons. This self-interaction is responsible for confinement in ways that the mathematics can describe but that remain conceptually difficult to fully picture. The gluon field between two quarks is not like an electric field. An electric field spreads out in all directions from a charge, weakening with distance. The gluon field between quarks does not spread. It is forced into a tube by the self-interaction of the gluons. A narrow flux tube of color field connecting the two quarks like a rubber band, except it never breaks. This flux tube has been modelled extensively in theoretical calculations and in lattice QCD simulations. The simulations show it as a cigar-shaped region of color field, connecting the two quarks and storing energy proportional to its length. The energy density inside the tube is roughly constant. Stretching the tube does not dilute the energy, it adds more of it. Stretch the flux tube and it costs more and more energy. Keep stretching and at some point, the energy in the tube is enough to create a new quark-antiquark pair from the vacuum. The tube snaps, but not into two free ends, into two complete bound systems. Two mesons, each with a quark and an antiquark, each color neutral, each permanently bound. You cannot win. The universe will not let you have a free quark. This is one of the strangest facts in all of physics. You can never reduce the problem of quarks to a simpler problem. In most areas of physics, understanding a complex system means breaking it into simpler parts and studying each one in isolation. You cannot do this with quarks. The moment you try to isolate one, the universe produces more quarks to prevent the isolation. The system refuses to be decomposed. Every attempt to separate quarks simply adds to the count of imprisoned quarks. The universe's population of confined quarks only ever grows. None escape. Now you know what quarks are and why they cannot escape. The next question is, were they always trapped? No. For roughly the first few microseconds of the universe's existence, quarks and gluons were not locked inside protons and neutrons. They existed in a deconfined quark-gluon plasma, not isolated individual particles, but a dense, hot, violently interacting medium. Not free in the sense of escaping far from each other. Free in the sense that the universe was so hot and so dense that the concept of confinement did not apply. The quarks were still interacting constantly with gluons and with each other. But the energy density was so extreme that there was no stable bound state for them to be confined into. Protons and neutrons could not form. Matter, as we understand it, could not exist. The universe was a plasma, not a plasma like the hot gas in the sun, where electrons are stripped from atoms but the nuclei still exist. A different kind of plasma entirely. A state of matter in which the quarks and gluons that would eventually become all the ordinary matter in the universe were roaming freely, colliding constantly in a dense, hot, almost perfectly fluid medium. This state is called quark-gluon plasma. QGP for short. Everything you have ever touched, every atom of every object that has ever existed, every planet, every star, every galaxy, was once part of a quark-gluon plasma. For 10 microseconds at the start of everything, the universe had no atoms, no protons, no neutrons, just quarks and gluons in an impossibly hot, impossibly dense state. Then the universe expanded. the temperature dropped. At roughly a few microseconds in, the temperature fell below a critical threshold, roughly 2 trillion degrees Celsius. Below that threshold, confinement switched on. The quarks began to bind. Quark-Gluon plasma condensed into protons and neutrons in a phase transition that produced all the ordinary matter the universe would ever contain. This transition was not slow. It happened over a period measured in microseconds inside a universe that was less than a second old. In that vanishingly small window, all the protons and neutrons that would ever exist in the observable universe came into being. Everything that would later become hydrogen atoms, then stars, then heavier elements, then planets, then you, was locked into its fundamental structure in the first fraction of a second. After the transition, the universe continued expanding and cooling. Within the first 3 minutes, protons and neutrons began combining to form the nuclei of the lightest elements, hydrogen, helium, and a trace of lithium, in a process called Big Bang nucleosynthesis. But the quarks were already confined by then. The nuclear structure was set. The universe today is far too cold for quark-gluon plasma to exist anywhere naturally. The coldest and emptiest regions of intergalactic space are warmer than absolute zero, but still billions of times colder than the 2 trillion degree threshold. There is no natural environment in the current universe that can recreate the pre-confinement state, except inside CERN. Most people know the LHC, the Large Hadron Collider, as a machine that found the Higgs boson. That discovery in 2012 was real and important. But the LHC is not only built for proton physics, it can also accelerate lead nuclei. A lead nucleus contains 82 protons and 126 neutrons. It is one of the heaviest stable nuclei in nature. That makes it one of the most particle-dense objects that can be accelerated and steered with precision. And when you accelerate 2 of them to close to the speed of light and crash them together, the collision is not just between 2 particles. It is between 2 dense clumps of hundreds of protons and neutrons, containing hundreds of quarks and gluons, all slamming into each other simultaneously. At the moment of impact, the 2 lead nuclei are not approaching as spherical balls. At speeds close to the speed of light, relativistic effects compress them along the direction of travel. Each nucleus is flattened into something resembling a thin pancake. 2 pancakes of lead nuclei colliding at 99.9% the speed of light, releasing the energy density required to dissolve the protons and neutrons they are built from. The collision produces thousands of particles. A single lead-lead collision at the LHC's top heavy ion energy creates a fireball that contains more particles than you could count in a lifetime. Alice tracks each one, reconstructing the history of the collision from the debris. The energy density at the point of collision is extraordinary. For an incredibly brief instant, the temperature at the collision point exceeds 2 trillion degrees. That is the threshold. That is the temperature at which confinement breaks down. The protons and neutrons in the lead nuclei dissolve. Their quarks and gluons are temporarily freed from their confinement. For a fraction of a second, a tiny bubble of quark-gluon plasma exists inside the detector. Not a large bubble, not long-lasting. The QGP created at CERN lasts for an unimaginably small fraction of a second, on the order of yoctoseconds, before cooling back into ordinary particles. It disappears and returns to ordinary matter before any instrument could directly photograph it. But it leaves traces. The particles produced as the QGP cools and hadronizes, the process of quarks rebinding into protons and other particles, spray outward from the collision point in patterns that are specific to QGP. Physicists can read these patterns and determine what happened at the center. CERN dedicated an entire detector to this purpose. It is called ALICE, a Large Ion Collider Experiment. ALICE was specifically designed and built to study heavy ion collisions and the quark-gluon plasma they produce. It is one of the 4 main detectors at the LHC, and its job is different from the others. While ATLAS and CMS look for new particles in proton collisions, ALICE recreates and studies the state of matter that preceded all particles. ALICE is an extraordinary piece of engineering. It weighs approximately 10,000 tons and sits in a cavern 56 meters underground. It contains multiple layers of detector systems, each designed to measure different properties of the thousands of particles produced in a single lead-lead collision. A single collision of 2 lead nuclei can produce thousands of tracks simultaneously. ALICE tracks each one. The detector measures the momentum of individual particles, identifies their type by how they interact with different detector layers, and records the angle and energy at which they emerge from the collision point. From these measurements, physicists can work backwards, reconstructing what happened in the collision and inferring the properties of the QGP that existed for the tiniest fraction of a second at the centre. ALICE has been collecting data since 2010. The upgrade completed during the LHC's Long Shutdown 2 between 2019 and 2021 significantly increased ALICE's ability to track particles and record data at higher collision rates. The upgraded detector can record the full interaction rate of the LHC, capturing more information per second than the original version. ALICE is studying the first microsecond of the universe, with better instruments than it has ever had before. Here is what shocked physicists about the quark-gluon plasma they created. Before the experiments, most physicists expected QGP to behave like a gas. The reasoning was simple. At such extreme temperatures, the quarks and gluons should be moving so fast and colliding so frequently that they would behave like a chaotic, largely non-interacting gas. Hot things are gassy. This is the usual rule. The QGP did not behave like a gas. It behaved like a liquid. Not just any liquid. The most perfect liquid ever measured. Physicists measure how easily a fluid flows using a property called viscosity. Honey has high viscosity. It resists flow and pours slowly. Water has lower viscosity. It flows more easily. Superfluid helium, cooled to near absolute zero, has almost no viscosity at all. It climbs out of containers on its own. The quark-gluon plasma produced at CERN has a viscosity extraordinarily close to zero, behaving like one of the most perfect fluids ever observed in any laboratory. It flows with almost no internal resistance. It behaves as close to a perfect liquid as anything physics has ever produced. This was unexpected. A substance at 2 trillion degrees, made of fundamental particles, flowing like an ideal frictionless fluid. The mathematics that describes this behaviour is borrowed from a completely different field of physics. The equations used to model how QGP flows were originally developed to describe black holes. There is a theoretical connection, discovered through string theory mathematics, between the behaviour of certain black hole horizons and the behaviour of strongly coupled fluids. The quark-gluon plasma is such a strongly coupled fluid. The same equations that describe how information moves around the surface of a black hole describe how the QGP flows in the detector. This connection comes from something called the ADS/CFD correspondence, a theoretical framework developed in the late 1990s by Juan Maldacena. It establishes an equivalence between a type of string theory in a particular curved spacetime and a type of quantum field theory on the boundary of that spacetime. In practical terms, It means that certain calculations about strongly coupled quantum systems, which are extremely difficult to do directly, can be mapped onto equivalent calculations about gravity in black holes, which are sometimes easier. The viscosity of QGP is one of the quantities where this correspondence proved useful. The theoretical minimum viscosity to entropy density ratio, calculated using the AD-SCF correspondence, is often written as 1 over 4 pi in natural units. Measurements of QGP viscosity at CERN suggest the actual value is close to this theoretical minimum. The QGP appears to sit near the boundary of what quantum mechanics allows a fluid to be. The viscosity was measured indirectly through a phenomenon called elliptic flow. When two lead nuclei collide slightly off-center, the initial overlap region is not a perfect circle, but an ellipse. If the QGP behaves like a fluid with low viscosity, the pressure gradients inside that ellipse cause the matter to flow outward faster in some directions than others, and this anisotropy is preserved in the final particle distribution. By measuring how strongly the outgoing particles cluster in specific directions, physicists can infer how easily the QGP flowed during the brief time it existed. The results were striking. The flow pattern measured at CERN's ALICE detector and earlier at the Brookhaven and Rick machine matched the predictions of nearly inviscid fluid dynamics far better than those of a gas or a weakly coupled plasma. The QGP flows like a liquid, a very strange, very hot, very short-lived liquid, but a liquid nonetheless. This is not an accident. It suggests a deep mathematical relationship between the most extreme state of ordinary matter and the most extreme gravitational objects in the universe. The connection is not fully understood as a physical statement about the universe, but the mathematics works with striking precision, and it tells you something about how strangely interconnected the different extremes of physics turn out to be when you look closely enough. The QGP is the hottest thing ever created on Earth. The coldest thing ever created is the interior of a superconducting magnet in a physics laboratory near absolute zero. Both extremes produce matter with unusual and extreme properties. Both extremes are being studied by physicists trying to understand the deep structure of nature, and the mathematics describing them shares surprising overlap. Here is something else the QGP experiments revealed. Something that nobody predicted with full clarity before it was seen. When protons collide at high energies, sometimes a quark or gluon inside one proton gets knocked hard enough to fly outward at very high energy. This energetic quark then undergoes a process called hadronization, recombining with other quarks from the vacuum to form a spray of particles called a jet. Physicists can detect jets easily. They appear as collimated streams of particles pointing outward from the collision point. In a normal proton-proton collision, jets appear in pairs back to back. If one quark flies out to the left, another must fly out to the right to conserve momentum. Two jets, two directions, balanced. In lead-lead collisions where QGP is formed, something different happens. One jet appears on one side, on the other side, the corresponding jet is significantly weaker, or in some cases, almost absent. The QGP absorbed it. The energetic quark flying through the QGP interacts with the medium so strongly that it loses energy rapidly. It is like firing a bullet into water instead of air. In air, the bullet travels far. In water, it stops quickly. The QGP is so dense and strongly interacting that it rapidly absorbs the energy of passing quarks. This is called jet quenching, and it is one of the clearest signatures of QGP production in the detector. One jet passes through relatively little medium and emerges intact. The other passes through the dense QGP fireball and gets absorbed, its energy distributed into the medium. The asymmetry tells you that QGP was there. You cannot see the plasma directly, but you can see what it does to the particles trying to pass through it. This is how particle physicists often work. The most interesting objects and states of matter are invisible to direct observation. They reveal themselves only through their effects on things that can be detected. The Quark-Gluon plasma exists for a fraction of a second at temperatures no instrument can directly measure. But it leaves asymmetric jets, specific particle distributions, unusual flow patterns, all of which are measurable. Jet quenching was first predicted theoretically in the early 1990s, before experiments powerful enough to test it existed. The prediction was that QGP, if it existed, would be dense enough to absorb the energy of passing quarks, producing the asymmetric jet pattern. When experiments at the Relativistic Heavy Ion Collider at Brookhaven National Laboratory in the United States first observed jet quenching in 2000, it was one of the key pieces of evidence that QGP had been produced. The CERN experiments with the LHC, which reaches much higher collision energies than the Brookhaven machine, produce a denser and hotter QGP. And the jet quenching measured at CERN is more dramatic than at any previous facility. The higher the collision energy, the more QGP is produced, and the more clearly the jet asymmetry appears in the data. The reading of those signs is the science. Indirect evidence, interpreted through theory, revealing a state of matter that no instrument can photograph directly. This is not a weakness of the method. It is how almost all of extreme physics works. You cannot see a black hole directly. You see the effects of its gravity. You cannot see dark matter directly. You see how it bends light and affects galaxy rotation. You cannot see QGP directly. You see what it does to the jets of particles that try to pass through it. Let us return to the phase transition, the moment 10 microseconds after the Big Bang when quark-gluon plasma condensed into protons and neutrons. This transition is called the QCD phase transition, QCD being quantum chromodynamics, the theory of the strong force. Before the transition, quarks and gluons in a deconfined plasma, not locked inside protons or neutrons. No atomic matter yet. After the transition, quarks confined in protons and neutrons, matter crystallized, atoms eventually possible. You exist on the afterside of this transition. Every atom in the universe exists on the afterside. The transition happened once, 10 microseconds in, and the universe has remained on the afterside ever since because it has continued to cool and expand. Never again reaching the temperature required to dissolve protons back into plasma. This transition produced something else. The protons and neutrons that formed from the QGP were not created in equal numbers with their antimatter counterparts. Every quark has an antimatter version, an anti-up quark for the up quark, an anti-down for the down. These antiquarks combine to form antiprotons and antineutrons. In the quark-gluon plasma, quarks and antiquarks existed together in nearly equal numbers. When the plasma condensed, they should have combined equally to form protons and antiprotons, neutrons and antineutrons. And then those protons and antiprotons should have annihilated each other completely, converting to pure energy. Matter and antimatter annihilate on contact. A proton meeting an antiproton converts both into a burst of photons, pure energy, with nothing material remaining. If this had happened symmetrically, the universe would contain no matter. Only a sea of photons, expanding and cooling, with nothing to form atoms or stars or anything solid. No atoms, no stars, no planets, no molecules, no chemistry, no biology, nothing, a universe of pure light, infinitely thin and infinitely cold, with no observer able to notice it existed. The universe we are in is not that universe, which means the annihilation was not symmetric. Matter won, by a tiny margin, by roughly 1 particle of matter for every billion matter-antimatter pairs. That margin is everything. But the universe contains matter. You are here. This means the transition was not symmetric. There was a slight excess of quarks over antiquarks in the plasma, roughly 1 extra quark for every billion quark-antiquark pairs. When the annihilation happened, a billion matched pairs cancelled. The 1 in a billion survivors were the quarks that became all the matter in the universe. Every star, every galaxy, every atom in your body, the product of that 1 in a billion excess. The source of that asymmetry is called CP violation, a bias in certain particle processes that slightly favours matter over antimatter. Physicists have measured this effect in quark interactions, and it is real and confirmed, but the amount measured inside the standard model is far too small to explain the observed universe. You would need roughly 10 billion times more CP violation than the standard model provides. Something is missing, some additional source of asymmetry that physics has not yet identified. The QGP phase transition is directly connected to this mystery. The moment quarks became confined is the moment matter crystallized from the plasma. Whatever created the asymmetry that let matter survive was operating during or just before that moment. By this point, you know that quarks are confined by the strong force. You know that QGP is the state before confinement. You know that CERN creates QGP briefly in lead-lead collisions. Here is the part that does not get talked about enough. Confinement is not proven. That is not a small statement. It is an enormous one. Quantum chromodynamics, the theory of the strong force, is one of the most successful physical theories ever developed. It makes predictions that have been confirmed to extraordinary precision. Its agreement with experiment is one of the triumphs of 20th century physics. But deriving confinement from QCD rigorously, mathematically from first principles has not been done. It is expected to be true. All the evidence supports it being true. Simulations on powerful computers strongly suggest it must be true given the structure of the theory. But a mathematical proof, the kind that would satisfy a pure mathematician and claims the prize money from the Clay Institute, does not exist. The absence of this proof is not a sign that confinement is false. It is a sign that the mathematics of QCD at the scales where confinement operates is extraordinarily difficult. The equations are strongly coupled at low energies, meaning the usual approximation techniques that work so well in other areas of physics do not apply here. The main tool for studying QCD at low energies is called lattice QCD. The idea is to simulate the behavior of quarks and gluons numerically on a grid of space-time points using a computer. By solving the equations on a discrete lattice and extrapolating to smaller and smaller grid spacings, physicists can extract predictions about how quarks and gluons behave without using the approximation techniques that fail at strong coupling. Lattice QCD calculations strongly support confinement. The calculations show a linear increase in the energy of a quark-antiquark pair as the separation grows, consistent with the flux tube picture. They show the masses of protons, neutrons, and other hadrons matching experimental values with high precision. They show the temperature at which QGP forms matching what Alice measures at CERN, but lattice QCD calculations are not a mathematical proof of confinement. They are numerical evidence. The difference matters. a mathematical proof would show, from the equations of QCD alone, without simulation, why and how confinement must occur as an exact consequence of the theory. That proof does not exist. The Clay Mathematics Institute named this problem the Yang-Mills existence and mass gap problem. Yang-Mills theory is the mathematical framework underlying QCD. Proving that Yang-Mills theory produces a particle spectrum with a mass gap, which is connected to confinement, and doing so rigorously from first principles, carries the $1 million prize. This is interesting for a specific reason. Confinement is not happening at small scales. It is happening at the scale of the proton. The proton is not an exotic, hard-to-reach object. It is in every atom in the universe. There are more protons on Earth than there are ways to arrange the atoms in the observable universe. Confinement is happening everywhere, all the time, inside every atom, and the reason it happens cannot be fully derived from our best theory. Physics has a word for this situation. It is called an emergent phenomenon, something that arises from the underlying rules without being directly deducible from them through simple calculation. Many things in nature are emergent. The wetness of water is not a property of individual water molecules. The temperature of a gas is not a property of individual gas molecules. These properties emerge from the collective behavior of many particles interacting. Confinement may be an emergent property of QCD in a similar way. It may arise from the collective behavior of gluons, from the way gluon fields tangle and tube and reinforce each other, in a way that cannot be simply derived but must be understood as a whole system behavior. What this means in practical terms is that the most fundamental observable property of all ordinary matter, the fact that quarks are bound inside protons and neutrons rather than roaming free, cannot currently be derived from our best fundamental theory without numerical simulation. The theory is correct. The property is real. The connection between them is established by powerful computers running for weeks, not by a mathematician sitting with a pen. There is something deeply unsatisfying about that, from a pure science perspective. It suggests that QCD, as we currently understand and apply it, is missing something. Not factually wrong. Missing a conceptual tool that would make the connection transparent. That missing tool may exist somewhere in mathematics that has not yet been connected to physics. It may exist in extensions of QCD that have not been explored. Or it may require a new way of thinking about quantum field theory that has not yet been invented. Understanding confinement from first principles is one of the outstanding problems of theoretical physics. It has been outstanding since quarks were discovered. It is outstanding today. CERN's Quark-Gluon plasma experiments have done something beyond just recreating an ancient state of matter. They have probed the rules that govern matter at the most fundamental level. Every time physicists create QGP, measure its properties, and study the particles it produces when it cools, they are testing the predictions of QCD in a regime of extreme energy density, where the theory has never been tested before. Some of what they find confirms QCD predictions beautifully. The onset of QGP at roughly 2 trillion degrees matches theoretical calculations. The overall flow patterns of particles emerging from the cooling plasma match QCD inspired models. The basic fact that QGP is produced at all confirms the theory's prediction that confinement breaks down at extreme temperature. But some things remain more complicated. The perfect liquid behavior, the near-zero viscosity, was more extreme than many models predicted. The exact value of the viscosity to entropy ratio of QGP is still being refined with each new dataset. The connection to black hole physics through string theory is unexpected and not fully understood. the jet quenching rates do not always match the simplest theoretical predictions exactly. What this means is that QGP is a probe of QCD in a regime that is different from any other. Low energy QCD, the regime of normal matter, is hard to calculate directly. High energy QCD, the regime of deep inelastic scattering where Bjorken and Feynman did their work, is more tractable. The intermediate regime of QGP, extremely hot but not infinitely energetic, has its own theoretical challenges. The ALICE detector is collecting the data that will pin down the properties of QGP with increasing precision over successive run periods. Every measurement is a test of QCD in conditions that existed only once in cosmic history. And here is the philosophical weight of that. The rules that govern how matter forms, how confinement works, how quarks bind into protons, are the rules that determined what kind of universe emerged from the Big Bang. If confinement worked slightly differently, if the strong force had slightly different properties, the protons that formed in the first 10 microseconds would be different. Different protons mean different atoms. Different atoms mean different chemistry. Different chemistry means no us. The specific rules of the strong force, the way gluons interact with themselves, the way color charge is screened at large distances, the way confinement enforces itself, are not arbitrary. They produce a specific type of matter with specific properties. And CERN is measuring those rules with precision that has never been achieved before. Here is the most unsettling way to think about everything we have covered. The universe spent the first 10 microseconds of its existence in a state where matter as we know it did not exist. Just a hot plasma of free quarks and gluons. That is 10 microseconds. The universe is now roughly 13.8 billion years old. 13.8 billion years is approximately 4 times 10 to the power of 17 seconds. The ratio of the QGP phase to the entire age of the universe is roughly 10 to the minus 26. That is 10 to the minus 23 seconds of QGP out of 4 times 10 to the power of 17 seconds of total age. For in effect the entire history of the universe, matter has existed. Protons and neutrons have been bound up. Confinement has been in effect. Atoms have been forming stars and planets and life. But that is not the natural default state of the strong force. The natural default, when temperature is high enough, is QGP. Free quarks. No confinement. No matter. The confined state, the state we live in, the state every atom in your body is in, is the low temperature phase. The cold phase. The phase the universe fell into when it expanded and cooled past the transition point and has been locked into ever since. You are a low temperature artifact of a cooling universe. The quarks in your body were once free, briefly. In the first 10 microseconds, then the universe cooled below 2 trillion degrees and they were locked inside protons and neutrons forever. This is worth pausing on. Every physical object you have ever touched, every material that has ever existed in the history of civilization, is built from atoms. Atoms built from protons and neutrons. Protons and neutrons built from quarks, and those quarks have been locked inside their particles since before any star existed, since before any galaxy formed, since before the universe was 1 second old. The quarks in the iron atoms of the Eiffel Tower have been confined since the first microsecond. The quarks in the carbon atoms of every living cell on Earth have been confined since the first microsecond. The quarks in the silicon atoms of every computer chip have been confined since the first microsecond. They were locked in. The universe cooled. and the confinement never lifted. In 10 microseconds, the universe set the structure of matter for the next 13.8 billion years, and CERN, for a fraction of a yoctosecond, undoes that. Not completely, not permanently. The plasma produced in the ALICE detector lasts for the tiniest measurable instant. Then it cools, and as it cools, something extraordinary happens. The free quarks and gluons in the plasma begin to bind again. Quark-Gluon plasma undergoes what physicists call hadronization, the process by which free quarks recombine into hadrons, the category of particles that includes protons and neutrons. In that cooling process, in the ALICE detector, physicists are watching a recreation of the first microseconds of the universe. The same process that produced all the protons in the observable universe, compressed into a bubble smaller than an atomic nucleus, for a duration shorter than any clock can measure. The particles that emerge from hadronization carry information about the plasma they came from. Their identities, their energies, their directions, the ratios of different particle types, all of these encode the properties of the state that preceded them. ALICE reads those particles and reconstructs the plasma from its debris. That moment of locking, the QCD phase transition, is the moment that matter as you know it came into existence. Before it, no protons, no neutrons, no atoms, no chemistry, no biology. After it, everything. The transition was not smooth or simple. The physics of how QGP condensed into hadronic matter, the process by which free quarks found partners and confined themselves, is not fully described by any theory. Lattice QCD calculations suggest the transition at the conditions of the early universe was a smooth crossover rather than a sharp phase transition. But the details of how billions of quarks simultaneously found partners and locked themselves up in the cooling plasma is one of the open questions in cosmology and particle physics combined. CERN's experiments are the only way to study this transition directly. You cannot go back to the first microsecond and watch it happen, but you can create a bubble of QGP in a detector, watch it cool, and observe what comes out. The particles that emerge as QGP cools in the ALICE detector are the same kinds of particles that emerged when the universe cooled 10 microseconds after the Big Bang. The measurements tell us several things. First, the temperature at which QGP forms. ALICE measurements place this at approximately 155 to 165 MeV in energy units, corresponding to roughly 2 trillion degrees Celsius. This matches the predictions of lattice QCD calculations remarkably well. The agreement between theory and experiment on this point is one of the successes of modern particle physics. Second, the properties of the plasma itself, its near-perfect liquid behavior, its low viscosity, its response to the energetic quarks that pass through it. These properties can be compared to theoretical predictions and used to refine the equations of QCD. Third, the particle yields. As QGP cools and quarks recombine into hadrons, specific ratios of different particle types are produced. The ratio of strange quarks to up and down quarks in the produced particles is higher in QGP events than in proton collisions, a signature called strangeness enhancement that was predicted theoretically before it was observed. This enhancement is one of the classic indicators that QGP was produced. CERN is a time machine. Not to specific historical moments, to the physical conditions of the first moments of creation. Every measurement from ALICE is a data point in the description of how matter came to exist. We have covered a lot of ground. Let us put it together. The quarks in your body are permanently trapped inside protons and neutrons. They have been trapped since the first microseconds after the Big Bang. The force that traps them, the strong force, is the strongest force in nature, and it operates by rules that physics can describe but cannot fully derive from first principles. The state of matter before confinement, the quark-gluon plasma, is the hottest state of matter ever created on Earth. It flows like a perfect liquid. Its behavior connects to the mathematics of black holes. It exists for a fraction of a second inside CERN's ALICE detector, and then disappears back into ordinary matter. The transition from QGP to ordinary matter, 10 microseconds into the Big Bang, is the moment that matter as we know it came into existence. A slight asymmetry in that process, the 1 in a billion excess of quarks over antiquarks, produced all the matter in the observable universe. The amount of CP violation that caused that asymmetry, the mathematical bias toward matter over antimatter in quark interactions, is larger than what the standard model of particle physics can account for. Something is missing from the theory. Some source of asymmetry that physics has not yet identified. And the strong force's most characteristic property, confinement, which imprisons every quark in your body inside a proton or neutron, does not have a mathematical proof from first principles. The best mathematical description of the strong force, QCD, strongly implies confinement, and every experiment confirms it, but deriving it rigorously from the equations remains unsolved. What does this add up to? The most fundamental fact about the matter you are made of, that it exists, that its quarks are bound, that protons and neutrons form, that atoms and chemistry and biology are possible, rests on a foundation that physics can describe, measure, and confirm, but cannot fully explain from the ground up. The prison that holds your quarks has no proven reason to exist, only a confirmed fact of existence. CERN is not just studying particles, it is studying the foundations of the fact that matter exists at all. Every lead-lead collision that briefly produces a QGP bubble is a window into the universe before matter. Every measurement of jet quenching, particle flow, and hadronization is a data point in the description of how matter emerged from the primordial plasma. This is what CERN disclosed something about reality means at its deepest. Not that they found a new particle. Not that they measured an anomaly in a decay rate. They recreated the state of the universe before the rules that allow your existence were in place. They measured what those rules look like when they switch on. And they found that the foundation is stranger, more mathematically complex, and in some ways less fully understood than almost anyone reports. Consider what that means. Physics has two major unsolved problems that connect directly to the QGP experiments. The first is the proof of confinement. Why do quarks stay locked in? The mathematics strongly implies it, and every experiment confirms it, but the rigorous derivation remains unproven, worth $1 million prize from the Clay Mathematics Institute. The second is baryogenesis. Why matter survived the Big Bang at all? The standard model CP violation is too weak by a factor of 10 billion. Something additional tipped the scales toward matter. We do not know what. Both problems are connected to the quark-gluon plasma era. The moment confinement switched on is the moment matter crystallized. Understanding QGP means understanding how and why matter became possible. CERN's experiments are not footnotes to particle physics. They are direct interrogations of why anything exists. The matter you are made of is an afterthought of a cooling universe. Before protons and neutrons existed as stable objects, the universe passed through a quark-gluon plasma phase. That plasma, not matter, was the universe's starting point. The atoms in your body exist because the universe got cold. Start with the simplest version of what we know. Quarks are real. They are inside every proton and neutron. They are inside every atom. 3 quarks in a proton, 3 quarks in a neutron. They cannot be separated. The force that holds them together gets stronger as you pull them apart. The energy you would spend trying to free a quark is spent instead on creating new quarks. The universe does not allow isolated quarks. This is not a guess. It is one of the most precisely confirmed facts in experimental physics. Billions of particle collisions have been studied. Quarks appear in the data as objects inside hadrons. They have never appeared alone. They have never escaped. Not once in the history of experiments has a free quark been observed. The confinement is total. The confinement is permanent. And the reason it exists, derived rigorously from the mathematics of the strong force, remains one of the outstanding problems of theoretical physics. $1 million has been offered to anyone who can prove it. The Clay Mathematics Institute added it to their list of Millennium Prize problems in 2000. 25 years later, the prize is unclaimed. The proof does not exist. The most important structural property of all ordinary matter remains mathematically unproven from first principles. The universe built an unbreakable prison before it was 1 millisecond old. It put all the matter that would ever exist into that prison. And it threw away the key so completely that the best mathematicians alive have been unable to formally prove the key ever existed. You are inside that prison now. Your quarks are inside it. They have been inside it for 13.8 billion years. They will be inside it for as long as matter exists. For roughly the first 10 microseconds after the Big Bang, this was not the case. Quarks were free. The universe was too hot for confinement to operate. Everything was plasma. Then the universe cooled below 2 trillion degrees, and the rules changed. Quarks found partners. Protons and neutrons formed. Matter came into existence. The phase transition that created matter happened once, in a fraction of an eye blink on the scale of cosmic time. CERN recreates a bubble of that pre-matter state in the Alice detector using lead-lead collisions at energies close to the speed of light. For a few yoctoseconds, ordinary matter dissolves back into plasma inside the detector. Then it cools and reforms. What physicists measure in that process is the most direct window ever opened onto the conditions that produced matter in the first place. And what they find is that confinement, the rule that locks your quarks in their cells, does not have a complete mathematical explanation from first principles. The best theory of the strong force implies it. All experiments confirm it. But proving it rigorously from the equations of quantum chromodynamics remains one of the outstanding problems in mathematics. The most important property of the matter you are made of is real, confirmed, measured everywhere, and not fully proven to exist from the ground up. There is something unsettling in that. The atoms in your body are built on a foundation that physics knows is there, but cannot yet completely explain why. You are made of prisoners, quarks, trapped inside protons and neutrons by a force that gets stronger the more they resist. Trapped since the first microseconds of the universe. Trapped until the universe either ends or heats back above 2 trillion degrees. The universe's default temperature is not 2 trillion degrees. It never will be again. Your quarks are not getting out, and the reason they were ever trapped in the first place is still, in some deep mathematical sense, waiting for a complete answer. Good night.